Hello and welcome to this homework help video. Here we're going to talk about two problems involving the solar system and other solar systems. So the topics are radioactive decay as a way to date our solar system, although the idea would broadly apply anywhere, and a particular problem about the techniques that astronomers use for finding exoplanets and specifically making measurements about those exoplanets. So number two, you can see it looks like a very small problem, has a lot packed into it. Number one covers a lot of space, but it actually uses fewer formulas, you might see. All right, so let's take a look, starting with number one, which is the half-life problem. So we're just going to go through it, go talk about each part and how we would approach it. So there's a lot of background information discussing the idea of half-life and how n, I'm going to highlight the key things I refer to, how n naught is the initial number of radioactive atoms. Okay, so that's going to be a key value that we have. We're actually only given it once. It never changes, at least of the one type of atom that we look at, one of the two. So then we're also given the half-life, which is represented by this variable here. So it's t, it's got a subscript of 1/2. Okay, so it's time, but with a 1/2. Okay, and that's measured in seconds. And then we have truly the variable t. So half-life is a constant. We're going to be given it, or maybe finding it in not this problem, but in a different version of this. But it's a constant. It's specific to some type of element on the periodic table. Whereas t is just how long has passed, or maybe how much time you think has passed. So the formula that we use for all our half-life calculations is this one here. Okay, this is an exponential formula, so it might be hard to tell, but if you look, we've got, so on the one side n, and that's on the left-hand side, that's kind of the product of the formula. On the right-hand side, we have the starting number. So n is the final number. This would be the final number of atoms that are left after radioactive decay. Then we actually have this multiplied by 1/2. So 1/2 in the language of math is called the base because it's what's being raised to a higher power. And the power that it's being raised to is t, that's whatever number we plug in for, divided by the half-life. Okay, so just divided by some constant, and we just call that t 1/2. All right, you can see here I write that subscript a lot smaller, making it hopefully more clear that t 1/2 is a constant, and we're just going to plug it in, make sure that it's in the exponent, and then we're dividing our variable by it. It's kind of hard to tell here because it's so large, right? It's hard to tell it's all the exponent, but indeed it is. Okay. Then there's some background about why zircon is particularly important for the study of dating rocks and specifically using uranium, which can exist in zircon and will become lead, something that lead not existing in zircon to begin with. Okay, so we got this very particular system. And by the way, that's so important for radiometric dating because you have to have some way of understanding that you're not just looking at a random mixture of differently aged samples. You know that everything, in this case, all the uranium in the zircon that turned to lead had to have done it through decay. There couldn't have been any lead to start with. So, so interesting that this particular rock lends itself to dating. Okay, of the many types of rocks out there. So, looking at the first question, part A, what additional information are we given? Because so far, let's think, we're just given the variables, but we have not been given any numbers, just some background information, which is what most of this paragraph was. Right here is just the background explanation. Okay, so continuing with the idea of zircon, we have a primordial asteroid. Okay, so that's the rock we're looking at. We think that it has a age equal to that of the solar system. So we're guessing that its age is going to be this. So in this case, that means that the t is going to be our input. So we're going to plug it in so that we can then have an estimate of how many radioactive samples there should be if this indeed is the correct age. So we're going to plug this proposed age in and get a number out that we could test. Okay? So that's going to be our value of T, as in the formula. We're also given the original amount of uranium-235. The fact that it's uranium-235 doesn't matter until part C, but hold that thought. And then we're also given the initial value of uranium-235. I shouldn't say value, the initial quantity of uranium-235. That's given to us in number of atoms. All of our quantities of substances here are going to be given as number of atoms. We never have to worry about doing anything that involves the atomic mass of individual atoms, and measuring like a larger sample of them, which is a version of this problem because you might not actually be able to count individual atoms. Instead, you actually have a weight, and you need to know how much each atom weighs, realistically, of course. So here, that's been done for us, presumably. So we know the number of atoms. It's a huge number, right? Even in a small sample. There's one other key bit of information, which is the half-life of uranium-235. It has a half-life, so that's that T1 half value, of 700 million years. Okay, and we're gonna be sticking with years in terms of all of our time measurements are being years. So yeah, there's no times we have to go back to seconds. So yeah, we're gonna do everything. Here I say it's measured in seconds, but here we can relate everything in years. So that's worth noting. Stick in years. Okay. By the way, the uranium-235 decays into lead-207. Okay, so what do we have so far in terms of what we can plug into the formula? Well, like any good formula, we're going to look at what we know and don't know. So what are our knowns and unknowns? Well, we definitely do not know N. That's actually what we're trying to find. Okay, so in part A, we actually want to find N. Okay, so that's what we were asked to find. Okay, we're given a proposed time, and we simply want to find out how many atoms we'd expect if the sample is indeed that old. Okay, so then we don't know N, which means the formula is actually immediately set up to solve for, considering that is our unknown. So what do we know? Well, we know N naught. Okay, we're given that as a value, 1.2 times 10 to the 22. No units on that because it is just a number of something, just counting. And then the other key information we have, two of them actually, is the age. We're actually going to plug this right in as 4.571, okay? And then we're going to also plug in the half-life. So T1 half, that's always a constant, okay? And that's, in this case, you always know. You're never going to have some unknown substance that you're going to be solving for its half-life. So it'll always be something you're given, the half-life value. And that's going to be 700 million years. So let's write this. Okay. So I left off scientific notation, actually, is what I want to do here. So this with the 700 would be 700 times 10 to the 6 years. So Y for years. With the variable, the time we're plugging in, I keep calling it the proposed time because it is, right? We're seeing like, what's our expectation if this time is right? Well, this one being billion would just be times 10 to the 9. Now, again, you often have to convert from years over into seconds. You don't here because if you think of the formula, you are just taking a ratio of those values. So whatever time unit it's in, as long as it's the same time unit, it's just going to cancel out up there in the exponent. Okay? So in this case, you have everything you need to plug into it. You just need to make sure that you actually are making, correctly putting the T over the T over T1 half, so the T over half lifetime in the exponent, and making sure you're raising 1/2 to that power. Okay, and finally, make sure you're multiplying by the original population, the N naught. That's going to give you how many atoms there are left in a sample that is that old, 4.571. Okay, now in part A, we're going to continue kind of with that same premise, the same idea, but we're going to say, well, turns out the sample that we have, we don't find that many. Okay, whatever number you got, I guarantee you it will not be this value. Okay, so now I'm going to give you the actual value, which is going to make you revise your expectations. So imagine you're a scientist, you thought this, was a primordial rock, but it turns out it's not that old. That means it must, have formed differently. Okay, so what do we don't know in this case? Well, the thing we don't know is T. Okay, so we want to find T. Underline it up here that we wanted to find N. Well, this time we want to find T, which is a bit more difficult. It, not terribly so or anything, but it definitely is the more tricky of the two because the formula isn't set up that way. I'm asking you to actually readjust the formula, solve for it. In terms of our values, we still have the same n naught, and we still have the same half-life. So n naught is still going to be 1.2 times 10 to the 22, and our half-life is still going to be 700 million. So 700 times 10 to the 6 years. Okay? The difference being here, of course, we don't know n, we don't know t. I don't know why I said we don't know n, because we do. Look, that's the thing. We've swapped out what we know. Okay? Before we had, we were solving for n, how many atoms there would be left. But this time, we actually directly measured how many atoms are left. You do that with actually weighing some sample, or getting an average of how many there are per sample. Okay, so in this case, different unknown. How do you actually approach it? Well, if you think about it, you have to basically solve for t. So what you need to do is you need to undo the fact that you have a 1/2, which means you need to take a log base 1/2. So you need to do a particular base logarithm in order to undo it. And what that will look like in a calculator step is that first you just need to divide both sides by n naught. So you're going to have n over n naught on one side. On the other side of the equation, you're going to have that exponent, the 1/2 raised to the t over t 1/2. But you need to find t, right? You need to get that out of the exponent. So what you have to do is take a logarithm of both sides. So what that's going to look like is it's going to be a log base 1/2. Okay, so calculators always have this option of doing a specific log. The default is always 10, but you're going to do log base 1/2. And if you do it to both sides, that will undo the exponent because that's what a logarithm is. Okay, so when you take the log base 1/2 of this whole thing, right, and this whole thing here, because it's all inside the function, then what you're going to get is you will still have the log base 1/2. You have to actually calculate this, but this will just be a number now, as long as you correctly input it into the calculator, n over n naught. But on this side, you've completely undone the exponent, and you're left with a great simple expression, just t over the half-life value. So of course now you're ready to directly solve for t. You just have to multiply both sides by your known value of half-life. So finally, moving on to part C. Okay, nothing new in part C in terms of using the formula. We're just going to introduce another decay that's happening simultaneously. So let me quickly summarize this. So in this case, we have a built-in cross-check. That's often the way it's described, because there, in a population of uranium, some small amount of it is 235, which we've been talking about. Most of it's actually uranium-238, okay? And that decays into lead-206. Now, that's great, right? That might be the one we care about more, but that decay is a lot longer. So it's not so great for ages that are just a few billion, because it actually takes 4.5 billion for just half the population to decay. Okay, and it really is more common for uranium-238 to be out there. It makes up 99.3% of any population on average, right? And well, that's what we're assuming here. So it's interesting about this problem is you still have the same n naught for 235. I'm going to have an extra subscript here. So that number never changes. I mentioned that before. So it's still 1.2 times 10 to the 22. But now, interestingly, it represents a tiny portion of the overall population, because now initially there's going to be a lot more of the 238. There's going to be, well, this exact ratio of it, right? Because we know that it's 99.3% is the 238. Well, that means that this value right here only makes up the 0.7%. Okay, so what we need to do is we need to have the correct ratio. So if we say then that this, I'm not actually going to write it out, because these ratios sometimes I'll find myself doing them incorrectly if I try to do it in my head. So I'm just going to say 235 or 238 or 235. That is the value, the bigger one on top. So as an exact ratio, not as a percentage, it'd be 0.993. Okay, cool. So then if we know the 235, we need to solve for the 238. So then the 238 is just going to be the, let's see, so, yep. that times the population, or we're going to be dividing by it, right? So let's see, because we have, does that make sense? Because if we multiply both sides and we have our n 235 over here, okay, that makes up the vast majority of it, okay? So wait, did I write this correctly? So if I had, it's that much bigger, so I'm saying that that's the majority of it is the 238. Because if it was always, or if it was completely the 238, then what would this look like, in terms of the percentage? So 99.3, there it is. So I'd say, well, it's equal to 1, right? Well, no, if it's equal to 1, then it's an equal ratio. Oh, okay. So that's yeah. So if I said, okay, well, this ratio one to the other, then I'm just saying they have equal amounts, but they definitely don't have equal amounts. So one over the other, we actually need to consider, okay, so for every 1 238, we have that many more. That's it. Okay. So we say then that for every 1 235, we have 993 of the 238. All right, so then if we were to solve for the 238, we see that it's exactly 993 larger, okay? So, because we have 99.3 to 1, okay? So, yep, basically out of a population of well, actually, no, hold on, because out of a population of 1,000, 993 would be that, and it would be a 7. All right. So it would be, sorry for working through this. It's just an interesting thing to think about. Okay. Yep. So there's 993 of the 238 for every 7 235. How do I know that? Well, I just thought about, okay, well, what is 99.3%, right? If it was just 100, you could say, well, if it was just this, I'd say, well, for every out of a population of 100, 99 are one thing, one is the other. But in this case, since we were down to the fraction of a percentage, we should actually think of a population of 1,000. So that's why we have 993 in the population of 1,000. How many are left? The other 7. All right. So actually, when you think about it, not that hard, but I was going at it in a number of different ways in my head. So anyway, so when we see that, then we can definitely realize how we would calculate it. So we would, I'm actually just going to do it right here, because I don't want to take up any more space. We have our n 235, and remember that's what we know. I didn't mean to use such a large eraser. And what we need to find is the initial population of 238. Okay, so we were not told that. So there we go. We just plug it in. Obviously, it's going to be a lot more because we're going to have that 993 over 7, okay, times the number that we know. That's going to be our new n naught, okay? Once we have n naught, what do we need to find out? Well, we're going to plug, we already know t, right? So we know t, so we're literally just going to solve for n. So our unknown is n, okay? And we're going to use the same t, and by the way, it's n238, okay? So in a sense, we had two unknowns, but in this case, we have two steps, right? We find the initial 238, and then we find the final 238. Why? Because we already know t. How do we already know t? We're using the same t that we found in part B. That value of t, our answer from part B, is one of our known values for part C, okay? And as far as any other known values, well, we've got the t1 half, okay? That's actually not even going to matter here. You're going to use your new t1 half because you only care about the decay of this, cross-check element, and that one is the billion one, the 4.50. All right? So there you go. That's your known half-life. Go ahead and find your final population, your unknown. All right? And as I said, your other known value is t. I can't write it down because it's whatever your answer to B was. Okay, so that is it for problem number 1. I want to briefly speak about problem number 2 because it's actually stuff we've seen a lot before, but it's coming all together with some new bits. I've already written everything down, so I'm actually just going to go through it and say what the steps are. Okay, so an exoplanet orbits a star with a known mass. Okay, so this is your mass of the star. That's how you discover exoplanets. Is you know something about their star. Okay, Then you notice that star is wobbling, which you're going to find out with the Doppler effect, and that's going to allow you to actually make a ton of measurements because we're going to combine that Doppler effect measurement with the transit method. All right, so I say, it's really a Doppler effect method and the transit method. All right, and so the information we have, let's go ahead and highlight it all real fast. So we got the mass of the sun, we'll definitely need that. We have the period of the orbit, okay, which is also the period of the wobbling star, because you can't find the planet directly. You have to look at the effect it has on the star, which is small. This here is actually the velocity of the star, which itself is actually measured from a change in wavelength, but we're skipping that step. But that would be a whole idea that we can use the Doppler effect, which is a formula we have seen, okay? But here we're just assuming it's already been done and the velocity's been calculated, okay? In this case, it would, it's not even like as so much a red shift or a blue shift because it's both. The star goes back and forth, sometimes towards us, sometimes away from us because it's wobbling on that axis in that direction, okay? And the very last thing is actually the mass of the person, because you're gonna bring this all together to find a weight, okay? So when you look at this problem, you're gonna use Kepler's third law. Definitely, Kepler's third law right there. Okay, that's going to allow you to plug in directly for that period because you know the period. Okay, now the biggest simplification we're actually making in this problem, and that's why I didn't write it so far, is this mass right here really should be the total mass, and then it's all these measurements should be relative to the center mass of the system. All of that can help things and make it better, but here we're using a pretty reasonable approximation. So actually use the mass of the star. Just plug directly in. That's going to allow you to solve for A. Okay, check that off your list. You've got the semi-major axis, approximately the radius of our orbiting planet. Okay, cool. We found that. That's the first thing that we needed to find. First part of this process. Okay, how do we find it? By using Kepler's third law and a known value of T and a known mass of the sun. Okay, well, a star, not our sun, some other sun, a star. Okay, by the way, gravitational constant, if you forgot, it's a constant, look it up. Okay, 4 pi squared, also just numbers. Okay, so that's Kepler's third law. This next step then, we're actually going to use the mass of the planet. Let's see, have we, oh no, we're going to find the mass of the planet with other things that we know. Oh, right, we're going to use A. I knew we used something. So it's the order matters. So because we found A with Kepler's third law, now we can use conservation of momentum, which I didn't label, but this equation, we'll put it over here. This equation right here is conservation of momentum. And there's a whole story of why we can approximate this as kind of linear momentum and not angular momentum, but it works pretty well. So again, some built-in approximations. Leave the refinements for the supercomputers. So conservation of momentum. Okay, well, momentum, pretty straightforward idea, just mass times velocity. The idea is, since it is a conserved quantity like energy, that the mass of the planet and the velocity of the planet have to be equal to the mass of the star and the velocity of the star. Well, we happen to know one of those directly, right, through the Doppler effect. We know the velocity of the star, okay? We know it's 11.2 centimeters per second. Make sure to convert that over to meters per second. We already know the mass of the star. We knew that through a number of other means. And check this out. You might say, oh, I don't know the velocity of the planet, but since you know its semi-major axis and you already knew its period, because whatever its period is must be the period of the wobbling star, because the wobbles caused by the planet's orbit, they're in sync, okay? So check it out. We now know A because of Kepler's third law. We already know T. And why can we replace the velocity of the planet with 2 pi a over t? Well, velocity is distance over time. Okay, D-I-S-T, short for distance. And the distance here is the circumference, 2 pi r, okay, except of course r is semi-major axis, right, be a little more accurate. And then what's the time? The time is the period of the repetition, the period of the revolution, the period of the orbit. So cool? That is everything we need to find the mass of the planet. So far we got the mass of the planet. Wonderful. So we actually don't care so much now about its semi-major axis and its period, because now we're going to zoom in and get right down onto it, because we care about a person standing on the planet itself. So knowing its mass was crucial. The other thing we need to know is its radius, because you can never know how heavy you are on a planet if you don't know its radius. You need to know its mass, which now we know, but you also need its radius. That's where the transit effect comes into play. Because the transit effect is this idea there's a drop in intensity being measured in watts per square meter. which is just energy per time per area, okay? We don't know necessarily what the actual wattage output of the star is unless we can fit it on the HR diagram somewhere, but we do know how much light actually reaches us, and we can see when that light drops off if the planet exactly comes in front of the star, thus slightly reducing the light that reaches us. So in this case, we have a tiny reduction in the amount of light of 0.00915%. As a ratio, by the way, that would be 0.00 and then two more, 0.00915, right? Because if you drop the percent. And that's basically what you want, because you want here the ratio of the area of the planet of the area of the star to be equal to, I say percent decrease in intensity, you actually want it to be the absolute decrease in intensity, okay? So you need to have whatever that ratio is, that drop is going to be, all right, this value here, right there, okay? Now, do you know anything about the star, right? Do you know the radius of the star? Well, you do, because let's see, all right, right there, I forgot to highlight it. It's kind of hidden in there, right? But it's one of our crucial bits of information. You actually know the size of the star. So that means you know exactly its area, okay? Which means you can calculate the cross-sectional area of the planet, which means you can find its radius, because both of these areas are just circles, because there's a slice, right? No, we don't have to worry about the the surface area of a sphere. It's just 2 pi r, okay? Squared, by the way, okay? It's not 4 pi r squared. It's not a sphere, because we're not seeing the whole spherical surface. It's flattened, essentially. Now, these things are so far away. So that's it. What does that give us? Again, that gives us the radius of the planet, okay? At least in the case, where if it was pointing to the planet, okay? So now we have the radius of the planet and its mass. That's all we need, okay? Once you know that, you can put yourself, theoretically speaking, on that planet and know how heavy you would be. Know what it'd be like to be on that planet. Would you, be crushed by its gravity? Would it, what's the story, right? Or would it be microgravity, like a little tiny dwarf planet? Well, then the last thing you need is, well, of course, the definition of weight being mg, because that is what you're being asked for. And then universal gravitation, kind of closely related to Kepler's third law, but it's its own thing, right? Which is just gravitational constant, mass of the planet, which you now know, right? Here I wrote it as uppercase, but same value. And then the mass of the actual person, you actually do know that. You're told 75 kilograms, okay? But here it cancels out, and you can find it later. But however you want to do it, you do know that. And then radius of the planets, which you just recently found with the transit information. All right, there you go. Solve for mg. Remember, mg is your weight. It's in newtons, and that's what you're being asked for. Okay, so hopefully that makes a lot of sense. I know it's a lot of steps, but it's pretty rewarding that you can fit all this information together to actually put yourself in the shoes of this, explorer or alien on this alien world, on this exoplanet. Okay, well, thank you so much for watching this homework help video. I truly hope it has been helpful.